Welcome back to HaloShift, where we peer into the future and dissect the tech that's shaping our tomorrow. If you're fascinated by what's next in the world of innovation, make sure you hit that subscribe button so you never miss the shift. Imagine you're searching for a single, perfect key in a warehouse filled with 1 trillion keys. A classical computer, no matter how fast, has to check them one by one. It's a brute force approach, but what if you had a tool that could examine every single key at once? A tool that didn't just guess, but saw every possibility in a single, instantaneous glance. Today, we're diving back into the most profound claim in modern computing, quantum supremacy, and the small, superconducting chip from Google that changed the game forever. This isn't just a story about a faster processor. It's a story about a new way of thinking. It's a story of a machine that, for a few hundred seconds, performed a calculation that the most powerful computers on Earth couldn't touch. We'll re-examine the physics, the breakthrough, and the global race it sparked. Get ready to have your understanding of what a computer is challenged. For all its breathtaking speed, every computer we've ever built, from the smartphone in your hand to the supercomputer simulating galaxies, operates on a simple, binary principle. It's a bit, a 1 or a 0, on or off. Our world of technology is built on a universe of tiny, sequential light switches. These machines are incredible at what they do, but their fundamental nature is limited. They are sequential thinkers, excellent for problems that can be broken down into a series of logical steps. But the real world, the microscopic world of atoms and molecules, doesn't operate in a straight line. It's chaotic, probabilistic, and mind-bogglingly complex. Think of a chemist trying to simulate how a new drug molecule will bind to a virus. The number of possible interactions, twists, and turns for that molecule is so vast that a classical computer would need thousands of years to get a truly accurate model. It's not a matter of speed, it's a problem of scale. The amount of information needed to simulate this behavior is simply too much for a system built on 1 south and 0 south. This is where the strange rules of quantum mechanics offer a new path. Instead of bits, quantum computers use qubits. A qubit is not a 1 or a 0. It exists in a state of superposition, a quantum state of being both 1 and 0 at the same time. The best analogy is a coin spinning in the air. It's not heads, and it's not tails. It's in a state of both until you force it to land. The second, and even stranger, principle is entanglement. When two qubits are entangled, their fates are linked. You can measure one, and instantly, the other state is determined, no matter how far away they are. It's a quantum connection that breaks the rules of classical space and time. When you combine superposition and entanglement, you get something truly revolutionary, a computer that doesn't just run a single calculation, but runs all possible calculations simultaneously. It's a librarian who can check every book on every shelf at the same time. This is the source of its power, and it's the foundation of a new era. For years, this was all just theoretical. The world of quantum computing was a playground for physicists, a collection of unstable, fragile machines that could only hold their quantum state for a fraction of a second. But a dedicated team at Google, working in deep secrecy, was trying to turn this theory into reality. Their goal was a moonshot. They wanted to build a quantum computer that could perform a task that was verifiably, demonstrably impossible for any classical machine. They called this milestone quantum supremacy. Their tool was a chip called Sycamore, a shimmering grid of 53 superconducting qubits, housed in a massive cryogenic refrigerator that cooled the chip to a temperature colder than deep space, just a few thousandths of a degree above absolute zero. The task they assigned Sycamore was not a practical one. It was a mathematical stress test, a puzzle known as random circuit sampling. The computer had to generate a random series of numbers and then verify its output. This kind of random data is a nightmare for classical computers, as they have to calculate each number one by one. What happened next was historic. In just 200 seconds, the Sycamore chip completed the task. And when the Google team ran the same problem on the most powerful supercomputer in the world, they estimated it would have taken 10,000 years to get the same result. The headline was everywhere: Google achieves quantum supremacy. The era of classical computing had a challenger. The race for a new kind of processing was no longer a theory. It was a reality, but the story isn't quite that simple. Almost immediately, IBM's arrival in the quantum race challenged Google's claim, arguing that with a few clever tricks and more storage, a supercomputer could have done the same task in just 2.5 days. They argued that quantum supremacy had not truly been achieved. This debate, far from being a setback, was a crucial part of the story. It was the moment a new technological frontier opened and the battle lines were drawn. Quantum supremacy was a shot across the bow, a claim that sparked a global, high-stakes competition to build the first truly useful quantum machine. So, if a quantum computer can't solve practical problems yet, what's the point? The point is the immense potential that a working quantum computer unlocks the kinds of problems that are currently impossible for us to solve. The first is drug discovery and personalized medicine. A quantum computer could accurately model the complex interactions of molecules in a way that is simply impossible for today's machines. This could lead to a new golden age of medicine, where we can design personalized drugs to treat specific genetic diseases and model the effects of a new medication before it is even tested on a single person. The second is materials science. We could design new materials with revolutionary properties, perfect superconductors that work at room temperature, super strong alloys for spacecraft, or incredibly efficient catalysts for green energy. A quantum computer could simulate the behavior of atoms and electrons, allowing us to build and test new materials in a virtual sandbox, a process that would take decades of trial and error today. Third, artificial intelligence and machine learning. The true potential of AI is bottlenecked by the sheer computational power needed to train massive models. Quantum computing could turbocharge this process, allowing us to create AIs that can discover new scientific principles, model climate change with perfect accuracy, or even create new quantum algorithms themselves. But the very thing that makes quantum computers so powerful is also their greatest threat. Their ability to solve complex mathematical problems also means they could break our current encryption. All of our online security, from our bank accounts to our private communications, is built on mathematical problems that are too hard for a classical computer to solve. A quantum computer, armed with a specific algorithm, could break that encryption in a matter of minutes. This is not a future threat, it's a current concern. It's why governments and tech companies are in a race to develop post-quantum cryptography, a new set of rules to secure the digital world from a quantum attack. The claim of quantum supremacy was not the end of the story. It was a prologue. The real race is now to build a machine that is not just powerful in a lab, but useful in the real world. The challenge is immense. Qubits are incredibly fragile. A stray electrical signal or a slight temperature change can cause them to lose their quantum state, a process called decoherence. This leads to errors that corrupt the calculation. For a quantum computer to be practical, engineers need to build thousands, even millions, of physical qubits that are constantly being monitored and corrected to create just a handful of perfectly stable, logical qubits. It's one of the biggest engineering challenges of our time. The competition is a new kind of Cold War. Google, IBM, Microsoft, and a growing number of well-funded startups are all locked in a race to solve the problem of stability and scalability. China has also poured billions into its quantum program, and every new breakthrough, every new qubit added to a processor, is a step closer to a new era of computing. This is a story that goes beyond technology. It's a philosophical leap. For thousands of years, we've relied on our linear, sequential brains to understand the universe. Now, we have created a tool that operates in a fundamentally different way, a way that mirrors the strange, probabilistic nature of reality itself. We have created a machine that can think in a quantum way, and we are only just beginning to understand what that means. It's a future that promises to solve problems we once thought were impossible, but it's also a future that forces us to reconsider the very nature of information, of reality, and of our place in it. So, was Google's claim a historic moment of triumph, or was it just the first shot in a new kind of war? I want to hear your thoughts in the comments below. If you enjoyed this deep dive into the strange and wonderful world of quantum computing, smash that like button, share this video with your friends, and subscribe to HaloShift so you don't miss the next big shift. This is HaloShift, and the future is already solving back.